Have you ever wondered how we have steady operations for devices that operate off batteries, considering batteries lose power over time, or how ICs that operate off 3 to 5 volts have steady and safe voltage, especially for microcontrollers? If the voltage dips or drops below its rated voltage, the system operation shuts down. If there is a spike, the microcontroller burns out. So how does the voltage powering these devices remain stable and reliable? They do so with the help of voltage regulators. They are devices or circuits which maintain a constant output voltage even in the face of input voltage variations, load current changes, or even temperature changes. They can be classified into linear and switching regulators. The switching regulators use high frequency switching to control output voltages. Examples are the buck converter, the boost converter, the buck boost converter, the flyback, and so on. They are very efficient compared to the linear type, but noisy due to switching. Let's focus a little more on linear regulators. Their design is simple and make them cheap. Also, they generate low noise but waste power, making them less efficient than the switching regulators. Examples are the 78XX series and the LM317 regulators. The 78XX series are fixed voltage regulators. They are obviously 3-terminal devices with pins as input, ground, and output. To get a regulated output voltage from the output pin, a voltage greater than the expected output should be placed on the input, both with respect to ground. The input voltage should be greater than the expected output voltage by a minimum of 2 volts. It's important to note this voltage difference between the input and output is given off or lost as heat, and this heat dissipated can be calculated by V in minus V out multiplied by I load, where I load is the amount of current pulled by the load. So the greater the difference between the voltage at the input and the voltage at the output, the more power loss or heat dissipation occurs, provided current remains constant. This regulator comes in variants. Some include the 7805, the 7812, the 7815, and others up to 7824. And the last 2 digits of these numbers mentioned are significant because they tell us the voltage these regulators give at their output. So let's take an example with the 7805. If we place an input voltage that is equal to or greater than 7 volts, we'll have 5 volts at the output. Here we're using a 9 volts power source. You should not use above 20 volts max input. We then add capacitors on the input and output to avoid oscillations. We'll use the 0.33 microfarads for input and 0.1 microfarads for output, as advised by our datasheet. Additional capacitors can be used for both input and output depending on the circumstance of use. Now, the LM317. This is an adjustable linear regulator. It also consists of 3 pins, with pin 1 as the adjustment pin, pin 2 as the regulated output, pin 3 as the input pin. The input voltage must exceed the output voltage by a minimum of 3 volts for this particular regulator. The output voltage is usually set by the use of 2 resistors. We see from the datasheet that arrow 1 should have a standard value of 240 ohms. Then we choose arrow 2 based on our desired output voltage using this formula. V out equal to 1.25 times 1 plus arrow 2 divided by arrow 3 plus I adjustment pin times arrow 2. From datasheet, our adjustment pin current is usually between 50 to 100 microamps. If we solve to find arrow 2 for 5 volts, we get 720 ohms. For 12 volts, we get 2 kilo ohms. So for this range of voltages, we can use a 5 kilo ohm trimmer. So we can adjust the trimmer easily to get any voltage that we desire. Note, for both regulators, if the voltage drop between input and output is high, and we're pulling high current, we'll need them on a heatsink. Heat dissipated here is same as V in minus V out times I load. So therefore, for our 9 volt power source and our 5 volts output, we'll be having 9 volts minus 5 volts times I load equal to 4 volts, which gives us 4 volts times I load. So if we would have it on a heatsink or not will be determined by how much current we decide to pull off the output.